Hi there, my name is Andrew Brown, and welcome to Capacitance and Capacitors. This video will start with an overview of capacitors and explore principally the relationships between capacitance charge and voltage. You'll see a thorough examination of dielectrics, and we'll finish up with capacitors arranged in series and in parallel. After watching this video, you should be able to answer questions like this one, which asks you to calculate electric field strength given some physical dimensions of a parallel plate capacitor. We're going to begin with an overview of capacitance, but before we break out the equations and circuit diagrams, it's worthwhile to review a couple things about capacitors. First, capacitors store charge at a particular voltage on their plates. For the purposes of the MCAT, all you care about is parallel plate capacitors, which are represented in circuits by the symbol here on the right. One example of a capacitor that you will undoubtedly encounter many times in your medical career is the defibrillator, which is used to treat cardiac arrest patients. When the device is turned on, charge is drawn from a battery into an internal capacitor. Then, once the clear signal is given, the capacitor rapidly unloads its stored charge to the pads, which basically act as wires, completing the circuit through the patient's heart. Now that we know a little bit about where capacitance comes from, let's quantify it and explore its relationship to other variables. In the capacitance equation, capacitance given in farads, which are coulombs per volt, is equal to Q, the charge in coulombs, divided by the voltage V in, you guessed it, volts. As we said before, capacitors store charge. Specifically, when one is connected to a power source, like a battery, current drives charges to the capacitor, at which point positive charge builds up on the plate connected to the cathode, that's the positive battery terminal, and negative charge builds up on the plate connected to the anode, the negative battery terminal. Now, while the equation we just saw helps us measure capacitance in a circuit, if you want to predict what capacitance will be given certain physical properties, you'll need to use this equation. Here, capacitance depends on the constant sigma naught, which represents the permittivity of free space. While we do give you its value here, you can expect it to be provided for you on the MCAT, so don't bother memorizing. A is basically just the area of the plates. We refer to it here as the area of overlap because all that really matters is the area in common between both capacitor plates. The last component is the distance separating the plates. In addition to capacitance, you might also be asked to calculate electric field strength in parallel plate capacitors. Remember, we define an electric field as pointing from positive to negative. The equation can be arranged to solve for the electric field or the potential difference. Electric field is measured in volts per meter, potential difference V is measured in just volts, and the distance d is again measured in meters. Just as in the rest of physics, when energy has been stored up, we say that there is potential energy. Therefore, we have another equation for measuring the potential energy of capacitors. Potential energy, U, is equal to half the product of capacitance, C, and the square of voltage, V. We can imagine that as current flows and the capacitor becomes charged, it will build up a voltage and a potential energy. This is just like what happens when a dammed reservoir fills up. The higher the water level, the more potential energy. Okay, so now that we've made it through the overview of capacitance and capacitors, we can introduce dielectrics. Generally, dielectric materials are insulators: air, glass, plastic, rubber, cotton, and on and on. As insulators, dielectrics prevent stray charges from crossing the gap, thus increasing the charge separation between the plates and therefore capacitance as well. We have an equation, too, for the change in capacitance due to addition of a dielectric. Here, C is the original capacitance, kappa is the dielectric constant, which, if we're talking about an increase in capacitance, must be greater than 1, and C prime is the new capacitance after the dielectric has been added in. When a capacitor is wired into a circuit, charge is flowing into it, building up on each plate. As you might expect, the addition of an insulator increases charge separation between the plates, which constitutes an increase in capacitance. So, when a dielectric is introduced to a circuit with a constant voltage source, the only mathematically allowable way for capacitance to increase is by increasing the number of charges stored on each plate. Let's do an example with dielectrics now. You're given a 5 microfarad capacitor that's connected to a 3-volt battery. Now the question wants to know what happens to charge, capacitance, and voltage when neoprene is added in, with its dielectric constant of 6. It's easiest to tackle this question by first looking at the 3-volt battery. That's setting the voltage, and so voltage will be constant throughout this problem. Next, you're going to want to figure out how charge and capacitance change once the dielectric has been added in. We can use the formula C prime equals kappa C. Substituting in our values, the new capacitance will be approximately 30 microfarads. Okay, so that's capacitance. Now for charge. Using the equation Q prime equals C prime times V, and substituting in our new capacitance and voltage, we get about 90 microcoulombs of charge. And that's it, because we have our three answers. The charge, 90 microcoulombs, the capacitance, 30 microfarads, and the voltage, a constant 3 volts. We're not quite done with dielectrics, however, because we still have to consider the scenario in which a charged capacitor is disconnected from the circuit. Turning to one of our equations for capacitance, the charge associated with the capacitor plates should be constant. After all, we have removed the battery, which normally shuttles charges around the circuit. When you remove it, however, the charges essentially just sit there, and thus Q is constant. Now, what about the potential difference? Since it is literally a measure of the energy difference between 2 points, a larger V also constitutes a stronger pull of charges on one side to the other. Thus, when a dielectric insulator is introduced, potential difference drops as the material shields charges from the attractive pull of their neighbors. And so, given the proportionality arrangements of the capacitance equation, a smaller denominator creates a bigger ratio, meaning capacitance and voltage are inversely proportional for a charged capacitor disconnected from the circuit. Okay, let's try another example now. Again, we are asked to calculate the charge, capacitance, and voltage across the plates of a capacitor. However, this time the capacitor is isolated, or disconnected from the circuit. Still, we're going to use the same capacitance equation. Rearranging to solve for Q and substituting in the given values of capacitance and voltage will yield 15 microcoulombs as the charge. Remember, this quantity will be constant, so the charge will be the same before and after the dielectric is added in. Now for capacitance. We were given the initial capacitance and dielectric constant, so finding the new capacitance is not too complicated. It should be 30 microfarads in this case. Notice now how capacitance has increased while charge was held constant. You should therefore predict that there must be a corresponding decrease in voltage. Rearranging the capacitance equation and substituting in the values of new capacitance and voltage, we get about half a volt. And there we have our three answers. Wow, so that was a lot on dielectric constants. We still have to cover some important rules, though, for both series and parallel arrangements of multiple capacitor circuits. For the capacitors in the series arrangement, just as in resistors, each charge pumped out of the battery flows through each capacitor. Thus, the current at each capacitor should be the same. Also as in resistors, the voltage drop across each capacitor will be different, with the sum of all drops equaling the total voltage. So, between capacitors and resistors in series, these two rules are the same. The equivalent capacitance rule is the one that's switched, so that for series arranged capacitors, capacitance adds reciprocally. This can be explained conceptually. As we know, distance is in the denominator of the capacitance equation, so when it increases, capacitance decreases. Here, the distances between each capacitor are said to add up. This leads to an overall dissipation of accumulated charge at each capacitor, and therefore a decrease in equivalent capacitance. Okay, so we just have capacitors in parallel left to consider, and then we can move on to practicing these concepts. As with capacitors in series, we will again start with some similarities to resistors. For the parallel arrangement of any circuit component, flowing current splits at each branch point such that the amount of current reaching each component is a fraction of the total. Voltage, on the other hand, will be constant across all the parallel components. As with capacitors in series, both of these rules are the same for parallel resistors and parallel capacitors. Equivalent capacitance, then, is the one that is different. resembling the method for calculating equivalent resistance in a series circuit. That is, the additive method. Here, notice that when more capacitors are present, the equivalent capacitance goes up. This can also be reinforced conceptually. If we line up all the capacitors in parallel so that they essentially become one long parallel plate capacitor, we have effectively increased the cross-sectional area of the plates of our new aggregate capacitor. Okay, that does it for the material this video is going to review. Now, let's put the concepts to use with a few practice questions. For this first one, you're being asked to compute electric field strength, given voltage and some physical properties of a parallel plate capacitor. The answer should be A. Using the relationship that voltage is equal to electric field times separation distance, we can rearrange, plug in, and get an answer. One thing of which to be aware here is the units. Remember, electric field is in volts per meter. So you might have to convert units in the future, like what we did here with millimeters to meters. Our second question wants you to describe how charge accumulation is affected by addition of a dielectric. The answer should be C. Now, we're not going to put up the dielectric equation because it's just the proportionality relationship we care about here. Capacitance increases as materials with greater dielectric constants are added. That's it. Thus, if capacitance has increased, so too should charge. Note, the capacitor is wired into a circuit, so voltage should be held constant. As charge is the only other variable in the capacitance equation, it must therefore increase. And now for the final practice question. Here, you need to find the dielectric constant of a material that is inserted into a 10 microfarad capacitor given the associated power source and charge increase. The answer should be C. In order to solve this one, first choose your equation. We probably want the capacitance equation in terms of Q and V because we are given those quantities. By calculating the new capacitance first, 40 microfarads, we can work backward to deduce the dielectric constant. Before we finish completely, let's take a moment to review the key equations from this video. We began with an overview of capacitance, stating that it is directly proportional to charge and inversely proportional to voltage. Parallel plate capacitors, the type with which the MCAT deals exclusively, can also be defined by their physical properties, namely area of overlap and separation distance. The strength of the electric field associated with a capacitor is a function of the voltage passing through it and the distance between the plates. The equation for potential energy depends on the capacitance and potential difference, or voltage. And dielectrics were shown to increase capacitance in accordance with the relationship shown at the bottom here. We finished up with a rather in-depth exploration of capacitors in series and parallel arrangements, so let's just review the most important relationships now. For capacitors oriented in series, current is the same everywhere. Voltage is additive, and equivalent capacitance is calculated by summing up the reciprocal capacitances and then flipping. Capacitors in parallel, however, will exhibit additive currents, voltage that is the same everywhere, and equivalent capacitance that just adds up sequentially. Thanks very much for watching, and good luck in your continued MCAT study.